Hello, everyone. My name is Mehul Motani. I'd like to welcome you to the third talk of the seminar series, Information Theory in Singapore. And also, if you're here for the first time, welcome to Singapore. Well, virtual Singapore, that is. As I mentioned last time, I wish that I could welcome you to Singapore in person, but these are strange times, so this e-welcome will have to do. Behind me is the view from my office. Pretty cool, huh? Actually, I wish this was a view from the Singapore skyline. So I really hope that this pandemic passes soon. We have a lot of good news with respect to vaccines and so on. So hopefully in the near future, all of you can visit Singapore, our beautiful country, and see everything for yourself. The Information Theory in Singapore seminar is organized by a team that includes Han Mao from NTU, Tai Kwei and Tang from SUTD, and me from NUS. And our aim is to promote, advocate, and spread the joy of information theory and coding theory within Singapore and around the world. After this talk, there are actually 2 more talks for the remainder of 2020, and we'll be putting out the 2021 schedule soon. So be on the lookout for that, and please do spread the word. Today is the third talk in our seminar series. Before we get going, let me address a few logistical matters. Please keep your microphone and video muted for the duration of the talk. If you have any questions, you can post them to the group chat, and we'll address the questions in the Q&A session at the end of the talk. Okay, now it is my great pleasure to introduce Professor Shlomo Shamai as our speaker today. Professor Shamai is a distinguished professor at the Department of Electrical Engineering at the Technion, Israel Institute of Technology. His research areas cover a wide spectrum of topics in information theory and statistical communications. He has received numerous awards and honors, and I won't go through the very long list, so let me just highlight a few. Professor Shamai is a renowned information theorist and winner of the 2011 Shannon Award, which is one of the highest awards bestowed to researchers in information theory. Professor Shamai is an IEEE Fellow, a member of the International Union of Radio Science, URSI, and an international member of the US National Academy of Engineering. I've known Shlomo for many years, from being terrified of him as a graduate student. Shlomo, if you want to know the story, I'll tell you sometime. Someone who thoroughly enjoys reading his groundbreaking research papers. The one thing that stands out about Shlomo, at least to me, is his breadth of knowledge and awareness of background and related work. It's quite amazing. Now I'm honored to have my colleague and friend, Shlomo Shamai, share his thoughts on Information Bottleneck, a unified information theoretic view. Let us warmly welcome Professor Shamai. So I'd give you a round of applause.
Thank you, Mehul. Actually, I'm a little, how shall I say, excited. Usually I don't give this kind of talks, but as you say, we are in a weird situation, so all the seminars are not physical. And I wish that I deserve part of your, how shall I say, part of what you said. I just wish that I would deserve those very kind words. Okay, so whatever we are going to speak about or to discuss about today is indeed the information bottleneck, and from a unified point of view, not specific like used in deep learning or other domains. And this general talk is based on several joint works which I did with my colleagues and co-workers for years. And here some are mentioned: Zaidi, Abdelatif Zaidi, Naki Algieri, Giuseppe Caire, Osvaldo Simeone, Sok Van Park. And And let's see what exactly we are going to focus on. First present and try to characterize and what is the information bottleneck from different aspects. And then, especially where it is used today, and then connections. Actually, the point here to show that this is a relatively new world, relatively, I mean, since 99, but it is the same and connects to many classical information theoretic frameworks and problems. And this is a very central part which mostly is not noticed. And then discuss the distributed information bottleneck and mainly its connection to communication. Actually, communication means 6G, where we have cellular system, and that's through cloud radio access network. And one of the main focuses of this talk is the last point, perspective. So with your permission, I'll try to skip details because of the time limit, because I really wanted to reach to the final topic, which I believe is interesting and important. Okay, the information bottleneck. What is it? And at the beginning, let me use the terminology of learning, of deep learning. We have here data, X, observations, Y, and the target, U, at the receiver. And there are two major quantities, which is the complexity measured by the mutual information between Y and U, and relevance. This is their terminology, and this is the information theory, rate and information. And relevance, how much information you has on X, again, in terms of mutual information. From the communication perspective, we don't have to actually justify anything, like the machine learning, the deep learning people led by Professor Tishby, math. Meaning, what is that? The relevance is exactly the information that I can transmit from X to U, where the processing in Y is oblivious, meaning that the one that processes Y doesn't know the code book, or if you want, the transmitter, the user, uses ideal cryptography, one bit key. So it can treat this like just the symbols, like a source. It cannot do any decoding because of knowing the code book that X uses. So this means oblivious. So this mutual information is exactly what can be done under the constraint that from the Y, the relay, to U, we have a finite capacity link, even optical channel, even 100 gigabits, still it's finite. So this, from our point of view, it's very simple. The notions and the meanings are immediate. Had we allowed the decoding in U, then the result would be trivial. The cassette bound, here it is. The rate from here to here is the minimum between the rate that can be transmitted over the channel, IXY, and the rate, the clean link from Y to U, which has the rate R. So that's not oblivious processing for this simple model is trivial. The bottleneck problem and the very notion, the terminology bottleneck, has been introduced by Tishby, not here, not in 1999. Okay, so it's not that I'm going to go through the details. Just the information bottleneck problem is quite used in many subjects and fields, not only information theory. Here I mentioned some. universality processing, reliability, delay, resource spread. How do you spread resources and allocation? Connectivity, networking, joint source channel coding, state estimation issues, universal decoding, modulation and demodulation, coding and decoding, equalization, scheduling, whatever you want, especially network information theory. That we will focus. Here I mentioned just overviews, very recent and serious overviews. Why? One by Gold and Poliansky, related more to learning. Another one by those myself and my co-author. Also overview, and this is more a general overview. And there are other papers. Just to mention about learning that I'm not going to detail, a very nice review paper by Simeone and others that connect to Information Bottleneck and others. Okay, let's go back to our problem. Again, with your permission, I will stick to those terminologies used in learning. X, the data are the features. Y, the observation. The encoder somehow encodes at rate R and transmits it to you. The decoder decodes that, and this should be the estimate of X. So the problem is, how do I preserve as much information as possible, given that here I have a finite rate? And so one question that in deep learning, could be raised: why do you measure complexity by mutual information? Why do you measure data rates by mutual information? Okay, that channel, but complexity. There are other complexity measures. For example, a very important one, Wapnick-Chernobynkins. And indeed, that's quite a problem. But remember, we are not focusing on learning problems. So for us, that's classical. We do source coding at rate R. So mutual information is a classical measure. So where do we stand? We have complexity, the mutual information between this and this, and relevance, the mutual information and this and this. So either we wish to maximize relevance under given complexity, or, of course, the complexity cannot be larger than the entropy of Y. Then you transfer Y as is, unharmed to you. Or minimize complexity under given relevance. Same thing, dual problem. Okay, very nice problem. Is it new? New, I mean 99? No, friends, it is not. And that I must say with maybe a word of caution. Many think it's new in the domain of learning. It is not, friends. Look what is the remote source coding problem. Look at X as the source. We don't see the source. We don't do source coding as we teach in information theory classes, because we don't see the source. We see it remotely through a channel. And now we can do source coding and code what we see. But the distortion is measured with respect to the source, not with respect to the C. And the distortion, in our case, not MMSC, a logarithmic distortion, measured by the conditional entropy of X given U. What is that? Okay? So we want to minimize. So the remote source coding, and we know the result. How can we know the result? Here, Dobrushin-Chibakov, 62. Not 99, 62, friends. Way before you were mostly born. Most of you were born. It's the minimum between Y and U under all channels U given Y, such that the distortion constraint is satisfied. What is the distortion constraint? We said the conditional entropy, but it relates to mutual information directly. X is given. So minimizing that means maximizing that. That's it. Exactly the same problem. Exactly. Not close, not almost, exactly. With the logarithmic distortion. And of course, later work, later I mean 75, Witzenhausen-Wyner gives the Lagrange, Euler-Lagrange equation that you find in the works of those of learning decades later. Is it all? All connections? No. How about of efficiency of investment information? Investment, you know. X is the stock market data. Y somehow correlated, carries information about X. Delta of R is what the late Tom Cover defined as the maximum increase in growth rate when var is described to the investor at rate R. Again, logarithmic distortion happens to be there. And it also relates, as Tom Cover has noted, to the classical Wyner-Ahlswede-Korner problem. So we have exactly the same problem. And solutions when X, Y are jointly binary, connected through a binary symmetric channel, or jointly Gaussian, has been made by whom? Elsa Erkip in her PhD with Tom Cover, 98. So, we have not done yet. How about common reconstruction? What is common reconstruction? The source coding, classical source coding, where the destination has side information, like Wyner-Zip, but we demand that the transmitter knows what is reconstructed. And the transmitter doesn't have the transmitter, the encoder doesn't have the side information, unlike Wyner-Zip. No, Wyner-Zip doesn't have it either, but it doesn't care about the reconstruction. Does have why? For example, a medical doctor. I want to know what the picture that the remote entity sees, because you know I want to know whether he sees the right thing. Okay, so this problem has been solved by Steinberg, Joseph Steinberg, my colleague. Again, what is that? This is minimize this. But when the reconstruction, you can use the site information to decode, but not to reconstruct. Reconstruct, you can use only Y. Okay, so you minimize this, you maximize this, because UY is exactly R. The rate that you have cannot be larger than R. You have this, and that's it. Bottleneck. Minimizing this means maximizing this, the bottleneck. And if you want, you know, that relates to Higard-Berger problems and others. How about information combining friends? Meaning, Y is the source now. Consider Y to be the source. And we ask, what is the information that Y has on U and X? Just because of this Markov structure, one can write it like this. IUY, we said it's R, the rate that we have. IXY is given because X and Y are defined. So minimizing this means maximizing this, the bottleneck, the relevance. Same problem. And where that appeared, for example, by work of Jacob Ziv, myself, and my PhD student of the time, Sutzkover. And we use that for what? Friends, belief propagation for LDPC code. Again, the very same problem. And if you want, don't read this paper. There is a beautiful overview foundation that trends by Land and Huber. We are far from being done. Hypothesis testing, classical statistics. Let us look at sequences and log sequences X and Y and length, IID sequences. And we assume there are two hypotheses. 8-0, they were produced from independent random variables. Here is the product of the distribution. H1, no, they are dependent with this distribution. X is available. The sequence X is available at the destination. And the problem is what? Yn not, but it is encoded at rate R. For n large enough as in our information theory business, Stein's error exponent normalized by n, which means classical Newman-Pearson that we teach in undergraduate, or the other problem, type 2 error, that is the sequences originally were governed by this, but we decided early this, is lower bounded by what? By this term. Maximum IXU under this constraint. This is the bottleneck problem. By definition, maxima irrelevance under complexity. And you know, quite a large view we have from Ahlswede-Korner, 86. Statistical decision making. How about wiretap channels? X input, Y the legitimate receiver, U the eavesdropper, and we have the degradation because of the Markov setting. The wiretap capacity a la Aaron Wyner, here it is. We don't need an auxiliary because of the degradation, here it is. No, but we will have a compound degraded wiretap channel. What do you mean compound? We don't know exactly what is the channel from here to here, but it can be any channel under a given constraint. So what is indeed then the wiretap compound capacity here? So here with my co-author. No, it has to do with the wiretap. At that time, we were not interested in bottleneck. So it's the minimum of this overall chance that satisfy this, again, the bottleneck problem. Why? This is given, minimizing this means maximizing this. So that it's not only the connection. This connection sometimes provide, you know, the way to have very elegant proof. For example, as I mentioned, if X, Y are binary symmetric channel, the bottleneck solution is also from Y to U is a BSC. Comes as a line from information combining that work with suit covariance. How about Gaussians that were solved by TGB? Okay. Here is another view, and I'll make it. X is Gaussian, Y is also Gaussian, Y is just X transmitted through a standard Gaussian channel with signal to noise ratio SNR. We know that the information bottleneck problem, here it is, a very nice problem. If R equals to 0, no rate, of course, then we have 0 here. If R equals to infinity, then U equals to Y. We have the standard Gaussian capacity, log 1 plus SNR. How do we prove this formula? And here I'll use the connection between information and estimation, IMMSC connection, due to Wyner-Ahlswede-Korner. Again, okay, Y and X Gaussian, we can then write X tilde is the square root of 1 plus SNR X, which is this, beta is just factor of SNR, and M is independent Gaussian noise, standard Gaussian noise. Okay, so information combining YXU, same as YX tilde U, we did nothing but scale, which is this. And here is the IMMSC result. What is this? It's the integral of the MMSC, minimum mean square, exactly, not bound. MMSC of y given the observation x hat and given u, because it's condition. Here it is, fine. Okay? We know that Gaussian, and for details, the foundation and trends that we wrote on the IMMSC, not on this, in general, it's very interesting. Okay, so that we can express like this, like the signal was Gaussian, but because it's not necessary, so there is a degradation. Gaussian inputs are the worst to estimate, the hardest to estimate. So there is an index row that reduces the power of the Gauss. Okay, fine. And row is something that we don't know what. And the variance, meaning when SNR is 0, is this. Okay, what is R? The complexity IYU, which is AY minus HY, the differential entropy of Y given U. HY is given, it's Gaussian, here it is. HY given U, again, we can connect differential entropy to MMSC. Here it is, the connection. And now we use what is known the single crossing point, which is critical. Means if you have a general random variable observed in Gaussian noise and the Gaussian random variable, which has less power. So we start at SNR 0, the Gaussian has less minimum mean square error, it's only the variance. At some point it crosses the real curve and then it's only one crossing. Then it's always above. So this is the result. Once we took it, identifies our row in terms of R, and that's it. And that's it. Then this is the information combining. And as we say, information combining gives the final result of the bottleneck. And you see, we can extend that to vectors using a more, how shall I say, a stronger crossing point, which applies to vectors. There is Bustin, Payaro, who is also now in Palomar, who is also now in Hong Kong. Okay, so that was I think a very beautiful, very different way to show results elegantly. We are not done yet, friends, with the connection, and all is the remote past. How about Wyner-Ahlswede-Korner problem? What is that? We have X and Y. They are encoded separately at rates Rx and Ry. For a given Ry, I give you Ry. What is the minimum Rx such that the destination can recover X losslessly? This is the result of those giants. Minimum, the conditional entropy. Here I write entropy, say X is discrete, not differential, under the information constraint. But that's exactly the bottleneck problem. I minimize this, I maximize the relevance. I maximize this because this fits. Here are the references, friends. Again, by those giants, all the three giants. Well, unfortunately, only Janusz Korner is with us today. Okay, scalars say scalar Gaussian, nice. What? But we are a vector Gaussian, you know, multi-element, multi-antenna. Okay, say X, Y are jointly Gaussian vectors. Same, the channel from Y to U that optimizes the information bottleneck is still Gaussian. But A is the matrix determined here. We won't go into details. Just the degree of the matrix, meaning the number of eigenvalues that are not zero, depends on the parameters. The larger in a way SNR, the more it is. All is closed form. This is the Tishby result, more elegantly, same result, but written more elegantly by Wickenbauer and Metz, presented at ISIT. Okay, very nice, the information bottleneck problem. Not enough for us, communication people. Input, relay, destination, that's not enough, right? We need something with many relays that are distributed and do not cooperate. What is that? Chief Executive Officer source coding problem. Here is a source, C and K encoder that wish to transmit information to the decoder that has to decode the source via given rate links R1 to RK, such that the distortion measure is again the mutual information that maximize the conditional entropy, which is to be minimized. Here it is, the log loss distortion, not MMC. The interesting thing that this problem is solved in general by Quartet-Weisman, while with MMSC distortion, much more classical, it's solved only for k equals 2. We don't know the solution for decades. So this distortion is actually easier. Let's skip the details how it is solved. And that is the central thing that we will use soon. Okay? So this connects what is known as the distributed information bottleneck, again shown here. So that solution of Weismann-Quartet which is more general. The classical information bottleneck is just a simple case, but still, this solution is given in general. Here is the theorem as from the Zurich seminar, appeared now already in a full paper, but of those authors. Here it is given. Let me, with your permission again, I skip the details. Just we need an auxiliary, a time sharing or resource sharing auxiliary. Sometimes is needed. In some example is not. Like, you know, like network information theoretical results or bound when we have all subsets of decay, but it's all. And again, with your permission, I'll skip the details just to say not all the world is Gaussian, for which we have an analytical way to determine that, as I've shown. Sometimes we do need to do the calculations and the parameterization through neural networks is a good idea, and the optimization here is shown via neural networks, skipping that. If indeed the world is Gaussian, meaning y and x are Gaussian vectors here connected through a Gaussian, MIMO Gaussian channel, then the general result reads clearly. Mutual information are load determinants, so on. We know everything. And we will use that soon. Of course, in general, distributed information bottleneck where there are quantization procedures, we need some more. And here is a recent work that describes that, 2005. Let's take an example. This CO or distributed information bottleneck is Gaussian, normal, standard, seen at both relays through Gaussian channels, symmetric to make things simple. They are connected each by rate R, again, same R, not R1 to R. And the decoder wants to decode X under the log distortion, meaning the maximize the mutual information of X hat to X. Here are the results. Closed form formula, this is the result. Not that simple, but close for. How about an upper bound? Upper bound, let both encoder cooperate. Then we have actually one encoder that has two antennas. The standard bottleneck problem. Standard, one, they cooperate. And we know, with this Gaussian simple exercise for undergraduate, you first sum y1, y2, you have the standard bottleneck problem with that result that we show here is the upper bound. A lower bound, those say, look, I don't care about the other one. Each does source coding at the rate R, and this combines the one, because they don't care one about it. Here is the lower bound. So we see here, this is the upper bound. The upper bound, of course, if R equals infinity, the upper bound is clear, because then this one has y1, y2. It's half log 1 plus SNR. This is this. If for R equals infinity, whatever we said, this is the theorem, the red line. This is the upper bound here, and this is the lower bound here. So, all close for. But one could say, look, sir, with all respect, you play with the bottleneck problem. But as you answered, your interest and ours as well is in communication, not in learning. So you refuse, you say those cannot decode anything of the code book here. Secrecy constraint, whatever you want. How much do you lose if they can, if you allow them to decode something? Very nice problem. So first, we do have the cut-set bound. They cannot do better if you do the cut here, y1 and 2, half log 1 plus SNR. You cannot do better if you have the cut here, 2R. You cannot do better if whether you have the cut here or the cut here, which is the same because of the symmetry. So here are the cut-set bounds. Okay, cut-set outer bound. But do we have a better bound than just this? Yes, we do. Quite complicated, quite, if I may say, sophisticated. The caution is because I'm one of the co-authors, but it's really sophisticated. This is a better bound. And the details, ITW, pass you. How about, okay, if you are allowed, find that you have upper bounds. What about achievable schemes? So far you do joint, distributed, compress, and forward. Then, of course, you mix the code and forward, compress and forward. And maybe that I'm thinking about jointly with the Professor Shirin Bidokti from the US about binning, list decoding, smart list decoding. But meanwhile, we can show that the code and forward is optimal here. If 2R is less than this, each user decodes that, one SNR, and they transmit to the destination either half of the information, coordinate. So together it's 2R, this is the capacity. You cannot beat that, you achieve the cut-set bound. Okay, friends, now we are reaching the point why we need all this for communication. A serious system, 6G cellular. Here are the cells. Here are the many users. Here are the channels that connect the users to each cell. Each cell can have massive MIMO, whatever you want. And the cells, unlike the system today I mean 5G included, when you decode at each cell all its related users and get heard by other users that interfere with that cell. And this damage is increasing because of the dense networks, more and dense networks. Doesn't matter the complexity. We cannot decode because After all, they are fired away. Most of the users that interfere us and remove them. So that is a block, a limiting block also of 5G. So what do we do in 3G? Decode nothing. Convey everything to the cloud that has to decode everything. This is the cloud ready access network. Let's skip the definition. And that's my central item of research for the last years. And the cloud ready access network, if you impose oblivious processing, which is nice also from the commercial point of view. Why? I don't care what is the standard. Change the standard. I don't care, it will work because I didn't build on anything the way you transmit code books and whatever. Oblivious processing. So we can characterize exactly what can be achieved with capacity in general. Exactly, not only Gaussian. Exactly. That's the work here. Exactly, which I think is a very nice result, including bounding the cardinality of the research sharing auxiliary queue. What's interesting, again, I'll skip exactly describing the details. Friends, what's top interesting? This is exactly the result of noisy network coding. Heavens, what has noisy network coding and net to do with this communication scheme? Actually, it has nothing to do, but you see it's the same. An amazing result. What can I say? And amazing, I can even say that it's an understatement. Okay, so let's demonstrate that. I said I've kept the formula. Let's demonstrate that. You know, a simple cellular Wyner model. 3 cells, all symmetric. Each user is connected to its own cell with amplitude 1 because the cell is closer, interferes to the other with amplitude alpha smaller than 1. That's the system. What do we compare? We compare single cell processing, 5G and 4G. The coding is done at the cell itself, interfered by others. Point-to-point forward compression. I don't care, I just compress the signal to send it to the destination. The optimal distributed form of compression, various aspects of that. And you used random coding. Who said that random coding is good? Here is structured code, linear codes, compute and forward done by Wyner-Ahlswede-Korner. And let's see what do we stand. These are the cuts and bound. The cuts and bound as a function of SNR. Again, the cuts and bound is very simple. We have a given rate per cell, so you cannot beat that. And that is where all the cells cooperate. So there's the standard the bottleneck thing. Here is the single cell 5G, useless because of the interference. Useless as SNR increases. This point-to-point compression. This is the distributed compression. Join the code and the compressor and the code, separate the compressor, therefore, not that big difference. And this is the structured coding, the Wyner-Ahlswede-Korner. So one can see and say, look, okay, we are more and more in higher SNR because of dense network. So with all your respect to generally, random coding, maybe we should use that. It achieves the cuts and bound. Again, even you show that, random coding is optimal, that's the work by the 4 of us. The answer is no, because here we cheat. Why we cheat? We took a fixed C. You want to increase rate, and rate increases had, say, C been infinity as log SNR, classical. Then you should also scale C as somehow as log S enough. Otherwise, you kill the system to start with. If you do that, here is a special example. Then this is the cut-set bound. And the computer forwards are not that good. Not that good because of the integer penalty without describing it too much. And here is the distributed compression. You lose almost nothing. The oblivious processing costs you almost nothing. You know what the practical implication of this conclusion? Do oblivious processing and that's all. From theory, the practical implication, my meaning is very, very strong. Okay, for learning, because of the time constraint, we are skipping them. I'm going a little to some perspective, well, another 8 minutes to go. You'll find we demonstrated here signaling X, Gaussian, very nice on the Gaussian channel. Also the distribute, we had closed form formulas, including that simple, example I showed. Beautiful. What about optimizing as we did since channel times, the input? What is the optimal input distribution under a given power constraint? In this scheme, is it Gaussian? For finite rate, RC, depends when no. Already has been demonstrated here that sometimes Gaussian is beaten by discrete. My conjecture, haven't been able to show it, unfortunately, is that the optimal distribution under power constraint is discrete. Of course, if C is infinity, it's Gaussian. That's not. It goes to Gaussian. That's always discrete. And, in general problems, we have bounds, as I already mentioned, the upper bound, where we don't impose oblivious processing. So I mainly discussed the uplink. Also in cloud radio access, we have duality properties as in the broadcast and multiple access channels. Here are the words. And interesting relations, much less clear than I presented at the beginning, is to Wyner's common information, God's corner work, whoever knows what it is, network source coding, as we mentioned noisy network coding, which is the same, and other problems that I'll skip. One interesting feature is robustness. Friends, it's very nice to solve classical information theoretic results, as we did here. But we need them for practice. And you see, some of the lessons, practical lessons that we convey we can convey to industry are central here, truly central. How about robustness? It's very nice, but who told you exactly that the channel is Gaussian? It's almost a good approximation. Okay, so I want to insert a robust measure to make the results not so sensitive to the assumption. And how do I do it? Not do I do it, how they did it. With a measure of robustness, which is based on the statistical Fisher information. Here it is defined. And now I optimize the standard bottleneck. Let's go back to the standard, which before this we didn't have, just the Euler-Lagrange, maximize this under the constraint, the Lagrange coefficient. Here I have another constraint by robustness. And amazingly, When X, Y are jointly Gaussian or vector Gaussian, still the channel from Y to U is Gaussian, the optimized channel. And that's nice. And as we already said, the IMMSC connection, I already demonstrated. It's very, very natural and insightful. It's not that I'm going to go through all that, maybe just one example here to say, look, we say source coding, everything, classical information theory, you take long sequences when the length goes to infinity, that's the result. And R, the rate, the backhaul rate is also, it's per channel use. So whatever N channel uses is NR. But what is the case if it's not one? Not that. I have long N sequences, but I can transmit just 1 bit, 1 bit. Doesn't scale with that. What about the bottleneck problem then? Beautiful, even in the binary case, unsolved. And the conjecture of Kumar, you just transmit 1 channel output and that and ignore the rest. When R equals N minus 1, you can transmit almost all, but 1, not N minus 1, not N. Then you transmit N minus 1 channel output, and that has been proven. That has been proven, the other, not. Very beautiful. And there are many things which continuous time models with filters that we discussed. Broadcast approach, classical, meaning that the relays, the source doesn't know chance state information as I assume, only the relays know. And still you want to achieve variable to fixed channel coding. What's that? Also, as you see, so one thing that I wish again to mention, why? Because it relates to what we said. Why do you measure, come on, you with your communication business? I'm interested in learning, forget your rates and everything. So why do you measure complexity by mutual information? A big question that was asked to teach me and not answered today, until today. Look about the following result. Very recent, unpublished by Linda, unpublished, just written 20. And he allowed me to present. The following result, okay, I have a data X, feature, and that's the feature, observation Y, and some measure, distortion measure from, I try to estimate X from Y, and this is my expected distortion, and this is the best one that can, not necessarily MMSC. Fine. MMSC is this one, where we have where the best processing is the conditional mean, that we know. Whatever we have under some conditions we don't mention is that the best distortion when you have Y, the measurement itself, and when you have U, which is transmitted from the measurement, here we have at rate R, for example, so it's larger. The difference is smaller than this quantity. Here we have mutual information. And what is this mutual information? Because of the Markovian, we write it this. This is the bottleneck result. Minimizing the upper bound means maximizing this. Meaning that the bottleneck result is important for any distortion measure. Doesn't matter what it is. Very important from a practical point of view. Let's keep the two-sided, more complex information system. Another thing, another distortion measure could be the entropy of flow, not the mutual information between Y and U. Why? I want to use LempXim. I don't want to do source coding, well, according to the statistics of Y. Very nice result. You can find them in the paper. And then there is no channel from Y to U. U is a deterministic function of Y, unlike the standard bottleneck. Very nice result. Let us finish the talk, but by the dual problem, the privacy funnel. What is the privacy funnel problem? We have the same thing, but now we want to minimize the mutual information between I, X, and you under the constraint that it is this, the mutual information here is R. Otherwise, you would choose mutual information 0, and then of course it's if this and this is 0 from here, from that to there is always 0 because of the data processing. Under R, what is the minimum? This is the frequency funnel. First, it immediately connects to the information combining. We maximize this, the standard bottleneck, by minimizing this. You want to minimize that, so you would have to maximize this. Classical. For example, the solution, which is for a BSC connection, we knew that the BSC connection is optimize the bottleneck. We know from that result by Shlomo Shamai and Zip that the other extreme is the erasure channel. Here you have the solution, immediate solution for the privacy part. For Gaussian, there are another example that actually you can show that this could be 0, even if this and this is hard. Okay, very nice. Not that complicated, but this solution, then we never bothered to publish it, or the Shlomo Shamai. Actually, it took me a while to understand that this solution actually solves what appears in a recent TCOM paper by Professor Lapidot, a very different problem. You have a classical Gaussian channel, but the receiver has also a helper that sees the noise and helps the receiver at a given rate R. And they showed that whatever you can achieve, which is the mutual information between X, Y, and U, use the output of the helper, is this. The classical capacity plus an immediate outcome for our observation of the pound, frequency pound, of the privacy pound. Okay, friends, I'll conclude here. I stole 2 minutes from you. Here in the slides that you'll find, how shall I say, quite a number of references, and it's not a conclusive set. The conclusive set, I would estimate 3,000 references. Underestimate, a little higher, but still the important one. And let me thank you. Thank you.
Thank you, Professor Shamai. Thank you, Shlomo. So can I ask the audience, are there any questions? If you have any questions, you can just type it into the chat window, please. And if you would like, I can also unmute you so you can ask your question, I mean, in person instead of typing in the chat. So we'll give everybody a moment to absorb everything you've said, Shlomo. Let's see, John, would you like to ask a question? Let me see if I can unmute you.
Hi, this is John from the computer science department. So yeah, it's interesting that this sort of same bottleneck problem has arisen in so many problems, even back to the 60s and 80s. I was wondering if, like, we get the same sort of formula all the time. I was wondering if there's also some deeper connections, say some operational equivalences or anything, where we can really transfer, say, coding schemes from one setting to the other. Or is it just the formula is the same and there's not much deeper?
No, not only the formulas. The formulas, actually, even the original formulas were motivated by practical setting. Given, the Dobrushin-Tsibakov at the time, the Russian problem in the 60s, they were motivated by practical settings, and in a way, look, to say the truth, the whole information theory starting from Shannon, was motivated by practical questions. but also algorithms that achieve that are shown. But the question is, those are very, very useful when we need that for communication. As we see, 6G is exactly that. And those kind of algorithms, of course, advanced, are really critical. And actually, how shall I say, if you see the leading companies, I mentioned Huawei, it's not only that, Qualcomm and whoever you want, they just beg for help, including, and sometimes because the result that we have now, not only theoretical results, are truly critical. And that's maybe an example, really, maybe a classical example, which didn't happen before, where information theory can impact seriously practice. Forget theory, forget academic, forget papers. And yes, definitely yes.
Shlomo, there's a question in the chat here. This is from Anshu Tendon. He's actually formerly one of my PhD students. So amazing talk by Prof. Shamai. Can Prof. Shamai kindly share these very informative slides with the group? If you're okay, Shlomo, would it be okay if I could get your slides and share them with the group?
Yeah.
So I'll contact you separately, and then
I'll send it over. No need to contact. I'll do
great.
it.
Okay, great. Okay, then there's a talk here from a graduate student, Leong Chek Ting. There are some works that use the information bottleneck theory to construct deep neural networks. What is your opinion about this application? Would it be beneficial to apply it on solving communication problems?
Yeah, definitely. Actually, not only that, as you see, I had some of them at the beginning of the talk, as I skipped them. Slides 2 and 3. So my opinion is that it's very, very, actually, some of their algorithms are very, very useful. It's not that I am just a big favor, this kind of an approach, but I must admit, some of the algorithms that I've seen and the talkers are mentioned in the slide are extremely useful, based on neural network, the way they build it and solve the general problem. Not Gaussian assumptions, so on and so forth, that we could bring closed form formulas. And those problems are important for communication. For example, things that I never even mentioned and do not appear on the slide, absolutely. Just state information. So one could ask, look, sir, very beautiful, and thank you for the very beautiful talk. Absolutely useless. Why? You assume that channel state information is given everywhere, so what is this? At best, I can use channel state information with some precision. And if you want to transmit site information to the destination, like 6G that you mentioned, it takes part of this backhaul capacity, C, to transform site information that you didn't say a word. What do we do? Actually, the answer is yes. So, and one of the results, take the simple problem. I'm sorry that I cannot write on the screen. I should have brought my iPad, but doesn't matter. That's what you can do physically, and you cannot do on the computer. So take the problem we had. Y x Gaussian scalar, to make it simple. Y equals the square root of SNR multiplied by a fading coefficient h, x plus a. And h, with all respect due, is not known to the transmitter, and neither to the destination. What does the relay knows it, because it has the antenna, it can measure. What does the relay do? here is the bottleneck problem that actually Professor Giuseppe Caire from Berlin and I have solved, and we are writing an ISIT 2021 submission, which solves what is the maximum between I, X, and U under the constraint. Now, the cost, the complexity is I, H, and Y given U, meaning there really has H and Y and has to transmit it in the optimal way. Quite different results. Very different approach. So you see, once you formalize the right problem, it has practical implications.
Shlomo, can I check? Is that like getting to like multivariate information bottleneck? Is that what you essentially are doing?
Yeah, actually yes, but you know, I'm seeking not algorithms to solve that in general, but analytical results.
Okay.
And here we managed to do, including interesting approaches, which very different from standard that you could imagine.
Okay, Shlomo, let me ask you a question. I recently came across a 1993 paper, which is called, I think that the title is Distributional Clustering of English Words. This paper is actually a precursor to the 1999 paper that everyone refers to. The variational principle is actually a precursor to that, is in this 1993 paper. It's by Pereira, Tishby, and Lee. I don't know if you know about it.
Yeah, actually,
it's an interesting paper. Yeah.
Tishby told me about that. I did reference it here. Yes.
Yeah, exactly.
I'll be grateful if you send it to me again, because
sure.
Somehow. No, I had it.
Yeah,
I had it, but when I prepared the talk, I managed to erase quite a few of references because I did something wrong.
No,
not only that.
No, your references are awesome. It actually
not only that. Many of the references that appeared, I managed to erase in my computer.
Oh, I see. Okay. So I had a question for you. Can you, because you mentioned at the end there something about deterministic channels. I'm wondering if you can say something about deterministic scenarios. For example, in supervised learning, often Y can be a deterministic function of X, right? There's only one right answer. So in that, one right classification, in that instance, what happens to the information bottleneck?
Still the general, yeah, of course, that's a very, very important problem. Where Y is a deterministic, not a special case. The channel is deterministic function. Not every channel has to be, statistical noise or something. The channel is deterministic function. Yes, in most cases, also from Y to U is a deterministic, not in all. Not in all. There are examples that still, it's even if Y is a deterministic function of X, from Y to U, better to have a random a channel, a random function, PU given Y.
Okay. There's a question here from John Tan. I'm going to unmute you, Changmin. You can ask your own question. So you can, hi Changmin.
Hi, Prof. Shlomo, it's a very interesting talk. Actually, I was quite curious in your last few slides. You mentioned there was a paper that mentioned discrete input distribution performs better. So I just want to find out, do you have any idea why this is the phenomenon?
Yeah, but because, look, let me make things simple. As I said, it's an open problem. Don't get me wrong. And I try to show it. I'm trying still, maybe that. But let's take the simple thing that will explain why, because of this finite C. Let's take the thing. Say instead of complexity measured by mutual information, I, Y, U, I take the complexity by the entropy of U. Okay, but the entropy of U, which is of course, if the entropy of U is equals to C, the mutual information is less because it's another terms. Okay, then we show that the optimal solution is a deterministic function. Okay, so U is probably a deterministic variable. It has a finite entropy. See, entropy, not differential entropy. It's a deterministic variable. Now, the classical observation in Gallagher's book, what is the optimal X that maximizes the capacity from X to U, where U is deterministic? It's deterministic with the cardinality not larger than U, that's it. But the general problem is not entropy constant. So that's the insight. And the example is already brought in that paper by Sutkover et al. Sutkover, my former PhD student, a decade ago. Okay.
Okay, are there any other questions for Professor Shamai? Okay, I think if there are no more questions, let's thank Professor Shamai again. We can, if you look in the Zoom interface, you can do, you can give a hand clap. So let's give a hand clap to Professor Shamai. Yeah, okay, or we can just clap.
Thank you.
Yeah. Thank you very much, Shlomo.
Nahul, keep me on the mailing list for future seminars, please.
Absolutely.
Yeah,
We'll do that.
definitely will.
Yeah, we'll add you. Next week is actually Raymond Young. Raymond's going to talk. It's the same time. It's 5 p.m. next Tuesday. And then the last talk is by Case in 2 weeks' time, also at 5 p.m.
Perfect. So it's, you have the talks and the abstracts. So keep sending it to me.
Yeah, absolutely. We'll do that.
Add me to the list.
Yep. We'll add you to the list. And then please feel free to send it to interested parties. Yeah.
Of course.
Yeah. I mean, I think if we can spread, information theory, I think there's, I mean, obviously the people who are here are already convinced, but I think information theory and that view, I think is very powerful. So
yeah, whatever I try to demonstrate, it's very powerful, even if you have no interest in academia, in papers, in research.
Yeah.
Just from the practical, from the industrial point of view.
Yeah.
It's very powerful, extremely powerful.
Yeah.
As it was never before, because of the advance of the technology.
Okay, again, thank you again for a really awesome talk. You are, in the words of one of the people I've been texting with, you're a master of storyteller. So thank you very much. This was.
I wish, some 5% of that was really true. I just wish.
Everyone here is convinced. So thank you very much again, and
thank you.
And we hope to see you at some of these seminars in.
Yeah, let's hope to see you physically at some point.
Absolutely, yeah, that would be great.
Bye bye.
Thank you.
Okay, bye bye.